assume we're recording. So, for those viewing this on the web, I posted a handout of a bunch of problems that we're going to be working with. There are far more problems in here than we're going to do during this review session. Some are separate problems and some are just copied out of the book. So when copied out of the book, I'll reference the problem number and page number. So for this review, which is exam 2 review, we'll be going over problems from the quality management lesson, from the logistics lesson, and from capacity planning. I think, and feedback I got from a lot of students, was that capacity planning and the logistics, that centroid method, which is the only thing we're going to worry about in the logistics chapter, was fairly easy. So I'm going to spend a little more time looking at the quality control examples, and we start right up in front here. So some different examples of sorts of problems that you might see on the exam and might have to work with. So the first one's on the first page, and essentially it's a lot like the X-bar and R-chart example from the slides. If we were to do something like this on the exam, again, I mentioned this in class, I'm not going to make you calculate all of the sample X-bars and all the sample ranges. That's just consumes too much frickin' time. So instead, I might give you something like this, which has all the raw data for 15 samples. In this particular example, 5 observations in every sample. But I pre-filled in almost all of the sample means and the sample ranges, and so this could test a few things. Can you do the very basics? Calculate a sample mean and a sample range. Can you convert those into the center lines, the X double bar and the R bar for the chart, and then give me the control limit? So we'll walk on through that. So the first part is, before you can do this one, you need to do the last 2 sample statistics. So for sample 14 and for sample 15, you need to give me an X-bar, which is the mean of that particular sample, and the range. This is not difficult. Anybody in class can do this fairly easily. So for sample 14 and 15, by calculating the means, and the folks who are here in the classroom are already crunching on some stuff here. For sample 14, by adding up those 5 observations and dividing by 5, you should come up with an X-bar of 0.503 and a range for that sample of 0.034. For those here in the classroom, if you're working through something and I put a different number up there, please stop me. I think everything I've got on here is correct, but nobody is perfect, myself included. For sample 15, then would be 0.506. And the range for sample 15, 0.023. And those, along with all the other sample statistics, now would allow you to start creating a control chart. First thing you need to do for a control chart, give me those 3 horizontal lines. The center line, which is the estimate of everything coming out of that process. And for that, we're going to use X double bar, which is just the average of the sample means, also the average of every observation in every sample. And then the control limits given to you by wait a minute. No, I haven't got it. Your handout does have, that's my solution. Yeah. The handout's got everything, it's pretty thick. So the handout also near the end has a page from the exam, which is just all the formulas, all the data that you need. The control limits given by the formulas are not like in a separate area, but down in the bottom of this table for all the control limit, the X-bar and R-chart control limit factors, the formulas for all the control limits. And so if I did make you crunch this, there is some number crunching. To get X double bar, you just got to use your calculator to add up all of the sample ranges, including the 2 you just calculated, and divide by, in this case, 15, because there's 15 samples. If we do that, 0.499. You may ask, how many decimal places on an exam? If I don't tell you, and you're working with numbers less than 1, you should go at least 3 decimal places when doing that. I try to, on all the exams, tell you how many decimal places to take it out. If you add up all the sample ranges and divide by 15, we should get an R bar of 0.035. So what this data here is telling us is our best guess, using this data, it's not a guess, but our best estimate of the average output from this process is a measurement of 0.499, and the best estimate of the range, the average range of measurements within a sample of 5 is going to be 0.035. These guys here are your center lines for the charts. The center line is the visual sort of representation of the average statistic from all the data that we've got. And looking at the handout, I haven't really asked you for anything, so we're going to go through and calculate all of the control limits for the different charts. LCL X bar and UCL, LCL and UCL of R. Use the formulas. I've got it on here, but again, use the formulas for those things that are found, forget the name of the exhibit here, but it will be on the exam, found on that table of factors out of the book. So we keep everything in the same order. So lower control limit and the upper control limit for the X bar chart, you can go to that, the formulas in that table. It's essentially the same formula with a plus and or minus sign. The control limits, theoretically, the idea is they're set a certain number of standard deviations of that sample statistic away from the average of that sample statistic. So we're going to set it a certain distance away from the average. We'll start with the average, X double bar, and for the lower control limit, we'll be subtracting off some number of standard deviations of the sample means. We don't have you crunching any of the real stats behind doing that. Mathematicians have done that, and they gave us those tables of factors, and we can use A2 times R bar. A2 is a factor in that table. A2 times R bar is an estimate of 3 standard deviations of the sample means. Don't ask about the math behind it. I don't want to do the math behind it. It's not fun. But by subtracting or adding A2 times R bar, we're getting control limits that are about 3 standard deviations away from the center line. If you want to do 2.5 standard deviations, 2, 3.5, you need a different table. So every one we create with this one table is going to be based upon an estimate of 3 standard deviations of those sample means. Find the formula. We've already got X double bar and R bar, and in some problems I'll just give you that, but in this one you would have had to calculate it out. 0.499 is what we start with each of them for the lower control limit. A2, got to go look it up in the table. It's not anything that you can calculate. Well, you could calculate it. Somebody calculated it for the table, but it's nothing that you need to worry about calculating. So the trick is, you go to the table and you've got a column that's A2, and there's a whole bunch of A2s in there. Which one do you pick? This always trips up students one way or the other. You'll notice that the very first column says the number of observations in subgroup. That's kind of a weird way of saying the number of items looked at in each sample. So when they're talking about a subgroup is a sample. So N is how many items are in each sample. not the number of samples. And I see it over and over and over again, where for this example, students will use n of 15, because there's 15 samples. N is 5, because there's 5 in each sample here. So when we go to the table, find the row for n equals 5, read over to A2, we get a value of 0.58. 0.58, if you want to put zeros in there. And might as well get the other two, D3 and D4, for the R chart factors. D3 is going to be 0, and D4, 2.11. And now it's just a matter of plugging and chugging what's going on over here. But plugging and chugging into the formula, lower control limit, 0.499, x double bar, minus A2, 0.58, times R bar, which we calculated 0.035. I'm going to move my formulas here because they're too close. The upper control limit is the same formula, you just add that there, 0.58 times 0.035. So 0.58 times 0.035, that's our estimate of 3 standard deviations away from the center line. And when you plug and chug and put all those numbers in there, your lower control limit should be 0.479. And your upper control limit should be 0.520. Has anybody here done that and can confirm? I've got it in a table, so I'm thinking Excel did this, and I'm hoping it's right. Should be. I've used this in prior exams, and I haven't changed it, so. I don't hear from someone in the audience that I've made a mistake. I'll just keep rolling on here. Control limits for an R chart are going to be based on a fairly simple, I haven't put it up here yet, have I? Fairly simple formula. The lower control limit for an R chart is D3 times R bar. And the upper control limit, D4. Use 2 different factors and just multiply times R bar. What's going on here? Again, some statisticians have done work in the background. These formulas are going to give you an estimate of R bar plus or minus 3 standard deviations of R. You'll notice D3 is a 0, and we'll do a P-chart example. And for both of those, essentially what we're doing, if we're into a chart for something that can never go negative, the formula might calculate a negative number, and in that case, we would just raise that lower control limit up to 0. That's what this factor is just doing for us by being set at 0 there. So lower control limit is just 0. 0 times R bar is 0. Upper control limit, 2.11. That's a D4 times our R bar, which is 0.035. You can start seeing when we're working with small numbers like this, you need to have your calculator doing more than 2 digits. Typically, I would go at least 3 and sometimes 4 if these numbers get really, really small. But in this case, that should be 0.07 something, right? 0.074. And so what you'd end up with is a template for creating your first or your initial control charts in this situation. So for an X bar chart, you would appropriately size the y-axis. The center line would be 0.499. We plot control limits on here at 0.479. And take it on up to 0.520. And these would simply become horizontal lines. When you plot a constant on a run chart, you get a straight line that runs straight across. And then we would take, and I'm not going to make you do this on the exam, I'm not going to make you create, I don't need to test whether you can put dots on a chart and connect it with a line, but you would take your data from the problem and start plotting out where all those X bars end up. So 0.494, there's one right there, 0.509, there's another one up there, 0.504, and so on. This is how this would work, 0.492, and then those are typically, excuse me, we connect the dots throughout time, and when you're done, you'd have 15 of those plotted, connected, and then the use for them, what we're trying to do is create an initial control chart. We'd interpret it to see whether or not it looks like it comes from a process that is under control, and if everything looks good, we would then use this control chart throughout time, and we would just keep adding samples to it and plotting them out. So a lot of times if companies do this on paper, and they still do, they'll have a long chart, a very wide one, and just continue plotting these things out throughout time, watching how the data is moving throughout time, looking for those special patterns, and we have some examples, and we'll address those later on, and drawing a conclusion from something we see that the process has gone out of control. Sometimes when you create an initial control chart, you see a pattern that indicates that this process was out of control sometime while we were taking these initial samples. And if you see that, the correct way to respond to that would be to take those samples, throw them out, because they're not representative of the process working the way it normally would, recalculate center lines, control limits, redraw it again until you have an initial or a trial control chart that looks like it came from a process that was under control. As these are used throughout time, what typically is done, whether it's done by computer or done on paper, as we get a whole lot of data points, what you want to do eventually, I'm not going to test you on this, there's nothing, there's no question on that, but just to reinforce the learning here, eventually as this thing gets really long with 100 sample points, they'll start reevaluating and recalculating center lines and control limits by eliminating perhaps the first 20 data points, once we get to 120 maybe. And we'll redo it with that latest 100 data points, getting rid of the first 20, and at regular points in time, we'll drop off the oldest data and recalculate things to adjust how the process is working at that point in time. So I'm not going to finish plotting this out. You could look for the most obvious most obvious pattern or thing to look for, looking for a sample mean, for example, if it's an X bar chart, or a sample range that is outside the control limits. Without even plotting, you can scan down your X bars and see if there's anyone bigger than 0.520. I don't see it. Anything smaller than 0.479. I don't see it. So to get any indication of any other pattern, you'd have to plot it out and look for those things. And we'll talk about what those patterns are a little later on as we look at something else. So, questions on that? Yes, Makila.
Okay, so how did you come up with the other two numbers for the sample mean, the last two numbers, 14 and 15?
That is just the average of the observations in sample 14 and sample 15.
Oh, so average of these?
That's it.
Okay, average of those. And then I know how to do the rest.
Yeah, each row is a sample.
Mm-hmm.
Each sample has a statistic,
Okay.
the mean of the sample and the range of the sample.
Okay.
Those are our quality statistics that we'll end up plotting.
Okay.
Other questions? Okay. I will move on. I know, Markeely, you're still crunching. But for our viewers out in TV land, I'm just going to keep going so they're not stuck sitting here. As we go to the next page, my solution handout is an excerpt. I want to make sure it matches my final handout here. Yes, the next page, I don't have that numbered. But the next one has a couple of very typical quality problems you might see on an exam or a quiz where we're using summary data. Instead of giving you all these tables, making you crunch statistics, there's very little value in that. So instead, these sort of word problems, very small ones, give you all of the summary statistics you need without giving you the detailed data. And these are things that can rather quickly be worked through on an exam. The biggest problem that students have here is picking the right data out of the problem and understanding what it means. So we'll work through a couple of those. At this point, hopefully you're reading the first one. Figure out what in the world we're going to be doing with this thing. So as we read through the first one, we've got Mars M&M Corp. Testing the packaging line to ensure that they're filling bags of their new vegan M&Ms with the proper weight. I don't mean to. Oh, anybody here a vegan? I don't want to go look at you, but you know. Okay. With the proper weights. This is it's a classic quality issue in any consumer food product, especially in the United States. Every can, every bottle, every box you buy has a net weight or a net contents on it, and there are consumer product laws that companies have to be essentially that specify the statistics and data that companies, the ranges that they can have as far as filling the product. So they take a lot of time checking the filling of the weights of packages to make sure that they're not underfilling. That gets them in trouble with the government, or consistently overfilling the package that just wastes product because they're delivering more than is promised. So we read through the problem. This particular line is packaging 1 pound bags. And they've taken samples of 10 bags each from the first 20 shifts that the new line has been operating. The average weight across all bags measured has been 16.07 ounces. The average range of measurements within each sample has been 0.04. I don't give you any one single bag measurement. I don't even give you in here any sample mean or any sample range. So I'm not wanting you to plot anything. What I want to do here is just, can you take some basic data and can you calculate a center line and a control limit? And another thing you might have to do is, what control chart's appropriate here? Well, I tell you the appropriate control chart. Calculate the center line and control limits for both X bar and R charts. So you know that that's what we're looking for here. Another way you could tell is that this data is not counting the number of defects or counting the number defective in a sample. That would be attribute data where we count things in integers. Instead, they're weighing something. It's a physical characteristic of each bag within a sample and then calculating statistics off of that. So variable data, the only control charts we do with variable data, X bar and R charts. So I erased my formulas. I erased everything, but I didn't need to do that. So I'm going to need center lines for both of those control charts that we would use for attribute data. I will put them back up here. Maybe I won't erase them again. But again, you go to the table with all those quality control factors, the bottom left corner, we have, not plus, minus, we have the formulas for them. X bar minus A2 times R bar, X double bar plus A2 R bar, D3 times R bar, D4 times R bar. No need to memorize any of that. Those are going to be on the exam. So again, we need to, what is A2, what is D3, what is D4, comes from the table, all depends upon N. So from the data that I give you here, there's only a few numbers in this, what is the value of N? There are only 4 people here, so it's going to be a little quiet. What's the value? You gotta be able to pull n out of this problem. What's the value of n? What? Is that a question?
No.
It's a statement?
Yeah.
Okay, you said 10?
Yes.
All right, either we have groupthink here or everybody's on top of it. It is 10. N is the number looked at in each sample. So this problem says it's just a matter of reading and comprehension. They've taken samples of 10 bags each. Each sample has 10 bags across the first 20 shifts. So it's 20 samples, but within each sample, there's 10. So if n equals 10, jumping back and forth from my tables here, didn't put it in my solution. N equals 10, read across A2 is 0.31. Might as well get the rest of them since I need them all. 0.22 for D3, 1.78 for D4. So I've got my factors, A2, D3, D4. I just need this X double bar and R bar. And sometimes I think students might get tripped up because this is actually pretty easy. What is X double bar from this particular problem? Marquila.
It's the average of the means.
Uh-huh.
You're asking me the number.
I'm asking you the number. Pull it out of this problem so you can put it in the formula.
16.07.
Why is there a question mark at the end of that? 16.07. The average weight across all of the bags, which is going to be the average of all the means, is 16.07. We subtract off of that A2, 0.31 times R bar. You're on a roll. What is R bar? The average of all the sample ranges.
0.04.
0.04. It's a pretty tight packaging line. The average range is 0.04 pounds, or I'm sorry, 0.04 ounces. So they're pretty tight. There's not a whole lot of variation. What's going on here, when we punch in the numbers, the lower control limit should be 16.058. When we do the 16.07 plus 0.31 times 0.04, you get 16.082. So this particular packaging line, if you look at, these are ounces, there's a whole lot of range between the upper and lower control limit for an X-bar chart. So this tells me, without plotting anything or anything else, this is a very consistent process. There's very little variation in the fill weight for the bags here. What would be the center line for the X-bar chart?
16.07.
16.07. It's X double bar. The center line of any control chart is the average of that statistic that you're looking at. So for these guys down here, we'll finish this up. D3, 0.22 times 0.04. That is pretty small, isn't it? 0.0009. No. 0.0009, right? I did not use Excel for this. I did it on a calculator before I came up. Am I right?
00. I had 0088.
0.0088?
Yeah.
I got one too many zeros?
Yeah.
See?
Might be 0.00.
Right. Okay. It looked like too many zeros to me. So 0.0088. So if I go to 3 decimals, I round to 0.009. Sorry, but if I want to go 4, because we're working in pretty small numbers here, so I should take it up a number. I think I've got the next one. I should have seen this when I was writing these down. 1.78 times 0.04. This time I've got 0.0712. That right?
I had 0.0071.
0.0071. .0071, something's not right, because this is an upper control limit, it's gotta be bigger than this one.
I got that.
I think the decimal, the number, the D4 is supposed to be .170 and not 1.70.
Nope, I don't think so. D4, go look it up. 1.78. Yes? Okay. So is this correct?
Yes.
Exactly,
Yeah.
yeah, okay, good.
Got it.
So we've got our center, the center line for an R chart is going to be R bar, the average of all the sample ranges. So the center line would be 0.04, with a lower control limit just above 0, and an upper control limit at 0.07. Questions? Marquila, how you doing?
How do you know which, if you're using lower control limit or upper control limit, like the equation, or do you find out all the
It
time?
depends on what I'm asking you for on an exam.
Okay.
In the real world, you're going to want both. You can't create a control chart without the center line and the control limits.
Mhm.
On an exam, I may ask you for just one number, then just give me the one number. If I ask you for both, give me both.
Okay, okay.
Okay, so on this problem, calculate the center line and control limits for both X bar and R chart. So I asked for all of them.
Okay,
That's why we did that.
okay. Other than that, everything makes sense. I was just looking for
Okay.
knowing.
Okay, any other questions? All right, so we can just keep moving on through here. The first two we did X bar and R chart. We looked at some data and did very little basic crunching, number crunching, calculated our center lines, control limits. For the next one, pulled summary data out, did the same thing, center line, which is given, control limits, which are pretty easy to get. The third problem, at the bottom of the second page, Luminosity Inc. Is worried about the quality of the new line semi-automatic under-cabinet LED lighting systems after a recent product redesign. You can tell that I wrote this problem or came up with it in the middle of a kitchen remodeling project, and I was putting in under-cabinet lights. But nobody here cares, apparently, so. So let's see what's going on here. They've taken samples of 100 lighting systems twice a day for the past 14 days. Okay, we have to pull something out of that data. In those samples, they have found a total of 98 defective units. They don't turn on automatically when they're supposed to. And that's the summary data that we're given. And from here, we can build or figure the center line and control limits for the appropriate control chart. The question is, what would be the correct type of control chart or charts to use for this situation? Here, a very simple test that is determining whether or not each item that is looked at is good or bad. The data is binary. Yes, no, good, bad, 0, 1. And essentially we're counting. So counting type of data is attribute data according to the book. We only look at, the book talks about P charts and C charts. We are using P charts. You don't try to pick between P and C. It's the only thing I test you on, the only thing we cover here. P charts are appropriate when we're counting up the number of defective items in a sample. And P is our sample statistic. P is the proportion bad within the sample. Some people would say percentage bad, but we're going to use decimal numbers, not put a percent sign after it, so P is a proportion if we're going to be mathematically or statistically correct. So this data is a P chart. What would be the center line and control limits for initial control charts based on 2 standard deviations? So remember I said for the X bar and R charts, we had a table of factors. That gives you control limits based on 3 standard deviations. For P charts, we don't have a table of factors because the calculations are pretty straightforward. So we can use the formulas we have for p-charts based on 3 standard deviations, 2, 2.5, 1.9, anything that you want, we can do that directly. For this, we want the formulas, so where are the formulas here? So on the exam, at the top of this, above the X bar and R chart factors. You have all of the formulas that we need. 1, P, the number of defects in one sample divided by the size of the sample. P is the sample statistic, that's the proportion bad. P bar, so let me just write it all up on here. In a sample, there's no bar across the top, that's a statistic for every single sample. And that's just the number bad or defective in the sample divided by the total number in the sample. You get a proportion. You multiply the proportion times 100, you get the percentage. But we're working with proportions. P bar, that's our statistic, so the center line is going to be the average of the statistic. P bar in this case, and that's the average proportion bad. There's a couple of ways you can do this. If every sample that you're looking at has the same number in each sample, you can just take the average of the p's, like we do for an X double bar on an X bar chart. And really, statistically, to be correct, we can only use the formulas in our book for consistent sample sizes, where every sample is the same size. So here, it could also be the average of the sample p's with a consistent sample size. Or the book gives you the formula in the slides, and this is the fail-safe one. You can actually use this with varying sample sizes, though it's not statistically perfect, but a lot of people will do that. The total number bad, so you're summing up the number bad from each sample, and then dividing by n, which n means the number in each sample times the number of samples. Or that denominator is total observations in all samples. So it's just another P, number bad over the number looked at, but it's the average across all of the different samples. That's our center line. We have control limit formulas. Given on the exam. These kind of take the form of the X bar control limits with the center line, P bar, and then you're going some number of standard deviations above or below, minus Z times S sub P, the upper control limit's the same thing, plus Z times S sub P. So we've got P bar, or we can get it real easy. We can calculate that pretty straightforward. What does Z stand for here? What does Z always stand for in stats? Not mathematics, what does it mean? Some of you guys have had stats over and over again. We'll talk about Z again when we get into inventory. Anytime you see capital Z, is statistically speaking, Z represents the number of standard deviations away from the mean or the average. So we'll revisit Z charts and pull data out of there, and we'll talk about it again. But Z is how many standard deviations you want the control limit away from the mean. You can set it to anything you want for a p-chart. What does this problem say we should set z to? 2. So it's based on 2 standard deviations. That's given. You never have to calculate it. This in more advanced classes, we might want to state a certain confidence level for interpreting p-charts, and you'd have to use that to figure out what the right z should be, but not in this class. It's always going to be given. So p-bar we'll calculate in a second. Z is 2. The last thing we need is S sub p. S sub p represents the standard deviation of the sample statistic p. And because this is binary data, we look to the binomial distribution for the standard deviation of a binomial distribution. So square root of p bar times 1 minus p bar divided by n. Boy, I got all the stuff that I need. So first I've got to calculate my center line, p bar. It's going to be pretty straightforward to do from the summary data. We'll use this formula here. Then I'll need to calculate S sub p, that standard deviation number, before I can do the control limits, because I need it over here. So let's work on that. P bar, total number bad in the total observations looked at across all these samples. So what's the total number bad here?
98.
98. Yeah, you guys should be screaming this out. That's the easy stuff. It's 98 because it just says so. Across all these samples, they found 98 that didn't work. How many did they look at across all these samples?
2,800.
Pardon me?
2,800.
2,800. Well, let me see. 100 units in each sample. 2 samples a day times 14 days. So 28 samples times 100. 2,800. And we'll plug and chug that number in. 90. Yes?
Yeah.
Again, this is crunching this calculator on my desktop, so as you can tell, I have been known to make errors when doing that. So we've got p bar, that's our center line. The average of the sample statistics, p. We want to do the control limits, but we need S sub p first, so we'll do that. So the standard deviation of those sample p's, 0.035 times 0.965, that's 1 minus 0.035. And we divide by n, going back to our summary data. They've taken samples of 100 lighting systems each. N is 100. Do the multiplication on top, divide by 100. Don't forget to take the square root at the very end. When I did this on my calculator, actually the calculator was in Windows, 0.0184. Can I get a hallelujah, amen in the audience here? They're working on it. The calculator's working so hard, it's getting warmer in the room. Got it? All right. So 0.0184 is the standard deviation of the piece. This by itself doesn't mean anything. We'll plug it in to get our control limits. So our lower control limit for the p chart here is our p bar, 0.035. Subtract off 2 standard deviations. So 2 times S sub p, 0.0184. And when I plugged and chugged, I got a negative number. Negative, not a very big one, 0.0018, just barely under 0. So, since we're going to be plotting the proportion bad in each sample, it should be obvious that we can't have a proportion bad less than 0. So it makes no sense to use a lower control limit less than 0. So when you get a negative lower control limit for p-charts, round it up to 0. So essentially, you can have a control chart. Well, you'll never see anything outside the lower control limit. And you might think a little bit and say, that kind of violates the whole idea behind control charts, right? We're looking as one of the rules to see things outside 3 plus and minus 3 standard deviations. In theory, yes, that works for something that's normally distributed. This is binomially distributed. But we're using the same sort of an idea based on the fact that the binomial distribution for large enough samples approximates the normal distribution. It's not perfect, and so that's why sometimes you'll get a lower control limit below 0. If so, just round it up to 0. The upper control limit for p, 0.035 plus 2 times 0.0184. And that's not something I'm going to do in my head probably today or any day. 0.0718 was the upper control limit that I came up with, and someone here is going to confirm that, and we're good. Again, these exercises with just summary data, we're not doing anything with charts. You can't interpret the charts. You can't interpret anything. This is just an exercise with short little data, quick, easy problem to show me that you can understand what the p-bar is, how to get it, understand how to calculate control limits to get those numbers. So, questions on that one? Marquila, I know I'm going fast. You hanging in here?
Yes,
Yes. This is going to be posted. You can watch it over and over and over again.
I'm gonna watch
As
it
much
today.
weekend time as you got, you can come watch my video. It's going to be just awesome. So, I'm going to leave some of this up here, leave all of this up here, right? Because if we flip to the next page, and I think this is going to be our last bit of calculating. Yeah, I got a couple more. You flip to the next page, you got something that's number 23. That's number 23 from the back of the chapter. And so we've got some raw data here, but it's a fairly easy one to work with. So you might see something like this on the exam. Even with the raw data that I give you, there's nowhere near as much calculations as needed for an X-bar and an R chart, because the data is much simpler. So, you can see by looking, and just right away when the problem says number of defective items in the sample in the raw data, without even reading the problem, you know it's a p-chart. 10 samples of 15 parts each were taken from an ongoing process to establish a p-chart. Well, you know exactly what chart because it tells you. The sample and the number of defectives in each sample are shown in the following table. So we've got some raw data here. I'm not going to write the raw data up on the board. It's right here. You've got it in front of you, whether you're here in the classroom or whether you're watching online.
What is that?
What's that?
Which problem
This
is
one
that?
right here. You've gone too far. Way too far. Way too far. You're still too far. It's just the third page of the handout. What? Okay. I take that back. It's the third page of my solution. What the heck is it? I'm sorry.
It's okay.
I was wrong. It is, sorry everybody, 1, 2, 3, and 4 are some control charts we'll look at in just a minute. That's not in my solution. So this is problem 23 on the 5th page of the handout for this review. Thank you for catching me on that. So we've got 10 samples, and you know, you can notice by looking at the data, there's 10 samples, there's very few numbers there. There's nothing like the data for an X bar chart. It's because for every sample, there's one number. For an X bar chart, for every sample, there's a number for everything in the sample. We're not doing that. We're not putting 0, 1, 0, 0, 0, 1, just kind of counting up is what we're doing instead. So I'm not going to throw the data up here because these are small numbers. We can do this probably in our head, well, some of it, as we work through it. So we want to get, actually here, we could calculate the P for every sample because we have the sample data. I'm not going to ask you to plot the chart, so there's really no reason to calculate all of those individual P's. If I asked you to plot the chart, then you'd have to calculate the P for each sample. If you did that, the P for sample 1 would be 3 divided by 15. The P for sample 2, 1 divided by 15. For sample 3, 0 divided by 15 or 0, and so on. But we're not going to go through and do that. Instead, we'll just run through the exercise in calculating center lines and control limits. Unlike the last problem, actually the last problem we had to calculate P bar 2. We need to calculate P bar here. That'll give you the summary data in the numerator, the total number bad. Well, let's count them up. It's a very simple data. 3 plus 1 is 4, plus 2 is 6, plus 3 is 9, plus 1 is 10. So across those 10 samples, there's 10 bad. Divide by how many we looked at in all those 10 samples. Every one of the 10 samples had 15 in it. So the total, 150. And when, I think that's 2/3, basically, or no, 2/3, 30, yes, that's 0.0. I got the solution here somewhere, 0.06666666, depending on how many decimal places you want to take that out. So the average proportion bad is 0.0667, if we were saying percentages, about 6.67%, but we're sticking with proportion. So we got our P bar. Next thing I need is the standard deviation of P so that I can plug that into my control limits. Square root of 0.0667 times 1 minus that, 0.9333, divide by n. What is n in this problem? 15. A number in each sample. It says n at the top of the table, so no excuse for missing that one. N is 15. At this point, it's a calculator exercise. I did this on my desktop, my calculator. I came up with this number. You guys check me. 0.0644. Wait for someone to nod to me before I continue. Got it? All right. I got my equal sign. And a lot of times students, again, will screw up by forgetting that square root sign. Don't forget the square root. So we got everything we need to do our control limits. Lower control limit for a P chart equals our P bar, 0.0667 minus Z. Is it given? It is given. So here's an example. If somebody stated a confidence interval, figured out what Z should be, but they still give us Z. They don't tell us Z. They tell us control limits based on 1.96 standard deviations. Z is just the number of standard deviations away from the mean. So it's minus 1.96 in this case. Times, oh, my calculations are wrong because see right now in my solution I used a Z of 2. I'll be real close, but I won't be right. 1.96 times S sub P, 0.0644. And again, I came up with a negative number. I'm a little off, but I didn't bring it, I do have a calculator. I mean, since I screwed up, I should do the work, right? Got my old-fashioned calculator in here. 1980s circa sharp made in Japan calculator that still works from my undergraduate days. So when I do this the right way, 0.0667 minus 1.96 times 0.0644. Come up with negative 0.0595. Again, it's a negative, makes no sense, just round it on up to 0 for a lower control limit you would use on a chart. My upper control limit would be the exact same thing with plus sign. And that's wrong in my solution too, so I'll calculate it and plus 1.96 times 0.0644. We come up with something that is totally wrong. Let me try it again. 10667 plus 1.96 times 0.0644 should come up with 0.19 something. Yes, 0.29, so call it, 29 if we're going on that far. And am I correct on that one? And since we had the raw data, we could create a control chart fairly easily. I'm not going to go through that. But you've got the control limits. You can ignore the lower control limits since nothing is going to be below 0. You can scan your data, but you'd have to calculate the individual P's and see if anything falls outside the upper control limit. It's not given directly there. But sample 1, 3 over 15, is 1 over 5, which is 0.2. So in the first sample, you've got one outside that upper control limit. You'll see it there again on sample 8. So even without drawing the control chart, I can tell that this data looks like it's from a process that was not in control at the time we collected all that data. What do you think? What don't you get? Yeah. P-charts are not that tough.
Yeah.
Doing the S sub P, it's just a little calculating. Don't forget the square root, and then all those formulas are given. Just take your time.
What is Z?
Z is the number of standard deviations away from the mean for the control limits. And it's given. So this problem, look at this problem. It says develop a P-chart for 95% confidence, and it says 1.96 standard deviations. That tells us that Z is 1.96. On exams, I typically just tell you, Z is this. All right, other questions? Yes, ma'am.
So for, this was Mars M&M.
Those vegan M&Ms?
Yes.
They're horrible.
So
Don't eat them.
for the lower control limit, upper control limit, it's all 16.07, then you work out the rest of the equation. Is that correct?
X double bar is given in that one. The average of everything is 16.07. So it goes where any formula says X double bar.
X double bar, okay.
And R bar, the average range was 0.04.
Mm-hmm.
That goes in every formula where R bar is.
Okay.
Other questions? We're gonna look at pictures now. Are you ready for picture, show and tell and everything? Hey! I'm doing this because I beat it in your heads during the lesson, either online or in the classroom, that there are several patterns of data that you might observe that you would not expect to observe from a process that is in control and giving you sample statistics that are distributed normally. And on almost every exam, there's like half the students only look at one thing. They lock in on 1 point outside the control limit. Well, hell yeah, that is an indication the process is out of control. It's not the only indication. So again, I refer you back to the book. There is one exhibit with a bunch of examples of typical patterns. It's exhibit 10.11. If you don't have the book, I don't know what to tell you because you're supposed to have the book. But you can basically think about things you would not expect to see when you're sampling from a normal distribution. And your sample statistics should be normally distributed. So outside the control limits means it's a number of standard deviations away from the mean. And the further you get away from the mean, the less likely it is to see something that far away from the mean if the process is consistent and normally distributed. So our X-bar charts use 3 standard deviations, which give us a very high confidence of 99 point something that if we see a plot outside the control limits on our X-bar charts, that process is out of control. There's a small, like 0.3% probability that, well, it's in control, but we're just seeing one of those rare things that end up that far from the mean. That's one, but the book gives you other things. A lot of them are based on, we expect the data to bounce around randomly above and below the mean. So you wouldn't expect to see a bunch in a row above the mean or a bunch in a row below the mean. That's like flipping a coin a whole lot of times in a row and getting heads every single time. Could be a fair coin. Good, you could flip a coin 20 times and get heads every time. Not very damn likely though. And that's the same idea in some of these data patterns. So we'll look at pictures. And so, you know, for the video, you've got this in front of you, and I'll bring it right on up and show you. But there's 4 sets of 4 control charts. And this is a classic exam problem that I'll have out there. Which one of these looks like it which one or which ones indicate that the process may have been out of control when these samples were taken. So we'll start with the first one on the top, and you should all have this in front of you, but here I am. I hope my camera's focusing properly. So which of these 4, if any, indicate that the process would have been out of control while taking these samples? Marquina.
D.
Which one?
D.
You took the easy one, D, right? Because D has 1 point outside a control limit. Everybody gets that one. That's nothing special. But you're right. So, you know, you're special. Just show me that and all that special. Is there anything else there that shows a pattern that you would not expect to see from a process that's in control and the statistics then are normally distributed?
C.
C? What's with C?
The point is very close to the lower control limit.
We have 1 point very close to the lower control limit, but it's not outside the lower control limit, is it? So you're going to have to go to the book and think and remember there's only a handful of these rules to look for. And if you get to the book and look at that rule, they don't have one that says, I see 1 sample outside the control limit, or within the control limit, but very close. That's not in there.
Okay.
Every once in a while, we would expect to see something, rarely, out near the control limit. So it's not C. Anything else that you think? It may just be 1, it may be more. Someone else here. Pick it on Marquis in the snow.
B.
Xander, you got something you're looking at? Oh, what we got?
B is consistently going down at the end.
Where, at B? So we're looking, the answer here is that B, we have a consistent drop-off near the end. And so, nice that you spotted that. There's a trend. The book says 5 in a row or more in a row headed in one direction in a trend. So I look at that, and typically you wouldn't count the top one, but just everything after that going down. And I'm counting after the peak. I'm counting 1, 2, 3. Oops. Down, and then the fourth one is a little up, and the next one is up. And so technically B would not be under those rules. We have several in a row. The book says 5 in a row, headed off in one direction. There's not quite 5. But you spotted it, which is good. And look for it, but remember 5. And so on the exam, if I want you to pick that, it's going to obviously be 5 or more. Anything else?
No.
No. Anyone else? No? No? What's your name again?
Chad.
Chad. Chad was right in looking at B, but for the wrong reason. What is it about B that violates those rules?
Does it have 5 in a row that are above the?
Yeah, we got more than 5 in a row above the center line, right? 1, 2, 3, 4, 5, 6, 7 in a row above the center line. What are the odds of seeing something like that in a process that's normally distributed? 0.5 times 0.5 times 0.5, 7 times. It gets to become a really small number. It's like just putting it, if you flip a coin 7 times, what are the odds you're going to hit heads 7 times in a row? Pretty unlikely. So 0.5 to the 7th. Chad's doing it. I'll do it. This old calculator.
0.78%.
The 7th. I have 0.0078. Is that what you came up with? So that's 0.78%. It's highly unlikely that when that data was taken, that process was consistent and stable. So for that one, you would want to be choosing the answers B and D. How about the next set of 4? Some of these just repeat themselves. So what we got, Marquila?
B,
B, why B?
because 5 in a row.
Yeah, so we got Chad answers. We got 5 in a row for B. On that second set of data, at the very end, what we've got are a bunch that are dropping off. And they continue to head in a downward direction. Is it possible to see that from a process that is stable and in control? Yes, it's possible. It's not very likely, and it gets less and less likely the more in a row you see headed off in that same direction. Anything else from those 4?
C.
What's that?
C.
C, why C?
Because there are 5 that are underneath.
Yeah, there's more than 5. 6 in a row below the mean when we look at C. So look at those right there. And I know a lot of students just don't, there we go, do not pick up on that initially when looking at these. And I've noticed that on exams in the past, like doing it in the exam review. Look at a bunch of them, try and figure it out. Flip the page to the third set. Which one's here? If any. Now we're looking at these.
A, there's 5 in a row below.
Okay, so A, center 1, 2, 3, 4, 5, 6 in a row below the mean, correct? You want to pick that one out, so A. Anything else? Your intuition's probably going to work here. What's that?
B.
B. Nothing outside the control limits, right? They bounce if they're above and below the mean, right? But they're all over the frickin' place. And they're all, most of them, pretty far away from the center line. This is what your book gives as an example of erratic behavior. It's something that's normally distributed. Most of what you see will be fairly close to the center line, the average. Almost nothing is near the average in here. So that's why that one would stand out. So for that third set, we have A and B. And in the last set,
B,
B, why B?
5 in a row.
5 in a row headed down. Anything else?
C,
Yeah, you're gonna get that one. C is so obvious. 1 point outside the control limit. You have one outside the upper control limit. I don't see any other issues with A. I don't see any other issues with D. So, interpreting control charts, you'll see something like that on the exam. So if you watch this review, you should do much better than you would have done if you didn't look at the review.
Would that be like a multiple choice kind of question?
Yes.
Yeah, that's what I was
Yeah.
thinking.
I'll give you a number of them, and, you know, A only, A and B, B and C, all of them. There'll be a whole list of things, but you just figure it out and then find the right answer, even if there's 10 answers. As long as you can figure it out, just find the right one.
Did we go over all the rules?
We did not, but we can go over all the rules. So again, from the exhibit, there's 10 pictures in the exhibit. There aren't 10 rules. The very first picture, an indication of normal behavior. Things just kind of bouncing around, nothing that is out of the ordinary. The next two, what they're showing are pairs of examples of the same rule. So the next two are the obvious ones, one plot above the upper control limit, one plot below the lower control limit. So those two are the same rule. Go down to the second row, where Marquila wanted to say, I see 1 point near the control limit. No, but if you see 2 in a row, very close to the same control limit, the upper or the lower. What does very close mean? The company's sampling plan will figure out where do we want this rule to apply. And so very often, in addition to the center line and control limits, they'll put dashed lines inside the upper and lower control limits, and those dashed lines would be the rules. See 2 in a row outside the dashed line, then that's an indication. They decide where those dashed lines are based upon their desired confidence levels, the risks of the type 1, type 2 errors. We would dig into that if this were a quality class, but we don't. So 2 in a row very close to either control limit. A run of 5 above the mean, the center line, a run of 5 or more below the center line. Indications you should do. A trend in either direction, and they don't give points here. Well, they used to say 5 or more in a row, heading one direction. Now they don't. They say a trend in either direction. They leave that kind of wide open. So maybe your first answer where I said, nah, there's not enough in a row, maybe you can interpret that and say that kind of, if I draw a trend line, it's definitely headed down that way. On an exam, it should be fairly obvious. What have we got? Then they talk about erratic behavior, points all over the place. That was that one that we looked at. And then the last one, I don't think they do a very good job of explaining it. The last one is an apparent shift in the average level. So I could draw something like that up here. So we expect to see points bouncing above and below the mean. Most of them fairly close to the mean, 60-something% within 1 standard deviation, 95% within 2, and so on. And we expect, if we looked at the whole chart, that everything kind of, if we drew a trend line through all the data points on the chart, it would be flat. So the last thing in the book where they say sudden change in level, again, I don't think they, where did I put that? Spinning around in circles here. See, you could have a control chart that looks like this. Control limits, and we could have a number of points going along like that, and then we could see like 5 more points where things kind of drop down. Kind of tough to see, but we've got a bunch that are kind of around the mean, and then it looks like things have dropped a bit. If is all visual interpretation and using your brain, but it looks like we haven't violated any rules yet, because 1, 2, 3 below, and then 1 that came above, and then 3 below. Haven't violated any rules, but if we see another point that comes up here, 4, and we're still below the mean. So the first half, I got a trend line which follows the center line. The second half, I got a trend line, if I were to estimate it, kind of down here. So that's what that last thing in the book is representing. It's a visual sort of thing. Oh, it looks like, although the rules aren't that we were up here and we're down here. And if that continues, the longer that continues on a control chart, the stronger the evidence. So you might have 4 in a row below, then another one that just jumps up, and then 1, and then 2, and then 3, and then 4, and you start seeing the pattern more clearly, that the average has dropped from here down to somewhere along here. Although no other rules are violated in there. Everything's within the control limits. We don't have 5 in a row below or above the mean, but you see that evidence that something's going on. Anytime you see the evidence that the process was out of control, when building an initial control chart, you throw out the samples that lead to that and recalculate. When using a control chart over time and you observe a pattern, so let's say this is an existing control chart with data that goes way the hell back here, and we start seeing this, at some point you stop and say, wow, I need to investigate this process. Something looks like has happened to drop the average output of the process. That is not a consistent or stable process if the mean drops. And the company would then investigate, go to the work center or wherever this is happening, talk to people, look at data, and examine the process to see if there's some explanation for this, with the goal of identifying some assignable cause of variation. This thing is wearing out, oh, this part loosened up, and we're not producing like we should, fixing it, and then getting the process and observing it to make sure it's back to where it was before. All right, so we're done looking at pictures, folks. There's, we could, we could do some more quality control, but I think we've probably hit as many as we want there. Or maybe I'll stick around later. So flipping through pages, there are several pages of quality control problems that you can work on if you want. On your own, you could email me your solution or your work, take pictures, or just send me what you think the answers are, and I'll tell you what's going on. And there are more examples at the website that are posted. I've got some Excel files that are there with basic data, and then I do everything to it. And you can work in Excel or print it out and work yourself to calculate the control limits and center line. And in Excel, you can very easily create all the sample statistics and build a chart, a run chart, in no time whatsoever, if you want to do that. And I've done that for a number of problems, those posted at the website as solved problems. So what I'd like to do at this point, where my watch is almost dead, so 6, we're at about an hour and 20 minutes or so, I'll move out of the quality control stuff. Next lesson on logistics, not a whole lot of problems to look at. We really barely touched on the topic of logistics. I mean, your authors could choose one decision within that broad field to focus on, that of facility location. And they present two basic sorts of concepts the companies use. I talked a lot in class about Amazon and HQ2 and their use of a factor rating system, which is the big picture thing that looks at all sorts of different factors. The company weighs each factor according to how important it is. Visit alternative sites. So for a factor rating system to work, there has to be a list of alternatives. Visit those alternatives, rate each one on all of the factors, and in the end, basically just sum up the totals for all the factors within a site, and the site with the largest total number is indicated as the best site according to that factor analysis. There's not a lot of problem where I'm not going to do an example of it because it's so darn simple. If I put one on an exam, so number 5, so this is in the handout for what would be the book page 479. Problem 5 in there talks about a manufacturer deciding to locate a new factory in the Northwest United States to serve blah, 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 growing demand. Narrowed the potential sites down to 2, city A and B, just like our slide example. It has developed a list of important factors and rated each city as shown in the following table, and we have some data. I'm not going to do this on the board because to solve this, you just add up the numbers for A, add up the numbers for B, and pick the one that's biggest. So I don't need to do that on the board. You can do that in your own time. If I put a problem like that on the exam, nobody should miss it because it's pretty straightforward. Problem 6 is a little more interesting and actually makes you think a little bit. So problem 6, I don't know where they came up with this one, but we have similarly another set of data, but according to as a result of a data crash in a computer, we're missing some numbers for one of the sites. Oh my God, what do we do to solve the problem of where to locate? And the idea here is, let's see how far apart these two cities are already, because we're missing data for 1, 2, 3 factors for city Y. Can we gain anything by looking at this? You can. One way to do is to kind of look at, well, if city Y on those remaining 3 numbers that are missing, if they got the maximum rating, what would their total be compared to city X? And we could crunch that all out, but I would look at this, if they get the maximum rating for transportation infrastructure, they would get 80, and they would gain 7 points over city X. Going down to proximity to customers, the max would be 65. They would gain 6 more points. 7 plus 6 would get them 13 on city X. And for the last factor, they could get 30, which would gain them 15. So 15 plus 6 before is 21, plus 7. They could make up as much as 28 points on city X. And I can look at city X and see that they're already ahead on the other factors by 7 on the first one, by 12 on the next one, that's 19, by 7 on the fourth factor, that is 26, by 6, they're ahead on everything else, by 6, 26, 6, 32, and by 5 points. So they're already too far ahead of city Y for city Y to make up the difference, even if they maxed out on everything. So that's the answer to that problem. Or completely, you would fill in the missing data with the maximum possible values for Y, a little asterisk next to them because we're just checking. You would calculate out then that even if city Y got the max on the missing ones, they'd still be behind city X. That's so straightforward. So you need to know the description of a factor rating system, and if I gave you something like this, you could add the numbers up and pick. A little more difficult is the analytical model that they present. It's only one. In fact, they present some other things in there, the transportation model of deciding what warehouse is going to serve what city. We don't cover that. But instead focusing on the facility location decision, the centroid method. For this, it's just analytical, so we're going to be trying to find a point on a map that would be the best location to essentially minimize transportation cost between the new facility and all the other existing facilities in a supply chain network. This is the classic, simple sort of a model. The book calls it the centroid method. It used to be called center of gravity. It's essentially the same thing. And there are a few problems in here that would fit that. So from the handout on the page that would be 481 in the textbook, problem 10 is an example. On the next page, well, starting at the bottom of the same page, number 11 and number 12. So 10, 11, and 12 are all examples of the centroid method. Let's do 12. Why 12? Because that's the one I have a solution for in front of me. But we could work the other ones too if you wanted to, real quickly. So number 12, Santa Cruz Bottling, soft drink manufacturer, Central California coast. Yeah, blah, 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 blah. Considering a new plant to serve the states of New Mexico and Arizona. So they're expanding into a new market. A key concern is going to be transportation costs. And that's a real concern for soft drink manufacturers because their product has relatively low value but relatively high weight. So there's a lot of cost in transporting this stuff for a low-cost item. We want to minimize that. Following a list of the cities where the main wholesale customers will be located along with estimated annual demand in cases of product for each. So this new facility is going to go on a map and serve 4 other demand locations: Phoenix, Tucson, Albuquerque, and Santa Fe. And to start this, we need our existing facilities and XY coordinates. So we take a map, put a grid over it, and design an X and Y grid. But more realistically, probably talk to the authors and say next time maybe just use longitude and latitude numbers, because you can Google that for any point on a map. But we have our X coordinate and our Y coordinate for each, and then a measure of how much business the new location is going to do and have to ship to the existing facility. So in this case, that measure is the number of cases. Could be number of cases, could be pounds, could be cubic feet, could be truckloads. In this case, the measure is the number of cases. And we've got 4. We've got Phoenix, Tucson, Albuquerque, and Santa Fe, California SF, the New Mexico Santa Fe. X coordinates of 250, 350, 800, 850, and then the Y coordinates 250, 125, 450, 520. Number of cases going to each, 25,000, 20,000, and so on. 28 and 17. So what we're trying to figure out is, on that same XY grid, where is a point that is going to minimize essentially the amount we ship times the distance it ships. So in this case, it'd be case miles that we have to ship things. And that's a good surrogate for the cost of transportation as a result of our decision. So to solve this thing, we go to the back, and it's going to be on the exam as for the formula sheet. If I can get on back there. We have the slide that I used in class on the top, and I decided this past year I hate this slide. Formula students look at it and say, what the hell does that mean? So I created the alternate one. I used it last semester when I taught my MBA class, and we hit this quickly. I think this one just is a little more intuitive. Either one, essentially, though, the same formulas. And what they're doing is we're coming up with a weighted average of the existing X coordinates, weighted by how much ships to each of those facilities, and a weighted average of the Y coordinates. That's all this is doing, is giving you a weighted average. So we need to sum up the total amount of stuff that's going to ship. And we're going to get a weighted average in the denominator of our ratio, we need the sum of all these volumes that are being shipped. And if I'm not mistaken, this works out to 90,000. If I am mistaken, all my answers are wrong. But I think I'm right. So using the formula given, the second slide pretty much tells you how to do it. You just sum up the product of each location's x-coordinate and the volume for that location. So you do if it's Excel, you're going to do a sum product. So for our new x-coordinate, C sub x, C centroid, sub x, its x-coordinate, is going to be 250. That's the existing, or that's the x-coordinate of the first facility times the volume we're going to ship to that new facility, 25,000. We'll just sum that up, do the same thing for all the rest of them. For Tucson, 350 is the existing x-coordinate. We'll weight that by the 20,000 cases that are going to ship there. For Albuquerque, 800 is the x-coordinate times 28,000 cases. And then finally for Santa Fe, 850 is its x-coordinate times 17,000 cases. You do see something like this on the exam, speed things up, knock off all the zeros. You could just do it that way. You could measure the volume in thousands, and you say you could do 250 times 25, 350 times 20, and then your denominator is the sum of all the volumes. So if you can do a short problem on the exam and you can drop a bunch of zeros, then remember to drop it from the sum too. But I'm not doing that in this example. You could do this on a calculator. It's just that when you multiplying with all those zeros, your numbers get really big, but it should work on any modern calculator. It shouldn't run out of space. And this I did on a calculator, so I'm going to hope you guys will double check me on this. Actually, I double checked myself by an alternative method I'm going to present shortly. 556, 0.67. And depending upon how big your grid is, maybe you just round it off and get something close enough. So as far as x-coordinates go, the x-coordinate of the best location is sort of right in the middle of all these. In one direction, it's going to have Phoenix and Tucson, and then the other direction, it's going to have Albuquerque and Santa Fe. Kind of right in the middle of those on the x, which would be the horizontal east-west sort of direction. C sub y, what's the y coordinate of the centroid? The exact same formula, but instead of using x coordinates, use y coordinates. 250, well, it's the same because our x and y are the same for p, but otherwise it's going to change. 25, now I'm going to go shorthand now. Plus 125 times 20. Plus 450 times 28. Plus 520 times 17. All of that divided by 90 since I'm dropping all the zeros off. And that will still work. And that will get you 335.44. With big numbers, this gets a little tedious. There's another way you can do it. It's just a weighted average, right? So we're weighting things by all of these weights and then dividing by the sum of the weights. Another way you can do this is for each location, figure out what percent of the total volume is going to be shipped to that location. We could start that way. So 25,000 divided by 90,000, 20,000 divided by 90,000. What percentage of the total volume is being shipped to each location? And we can use that in a shorter formula. So if we do, the P, I don't know, P sub W, P sub volume, what proportion or percentage of the volume is going to each location? 25 over 90, again, I'm dropping the zeros, 25,000 over 90,000 equals 0.2778. And then doing the same numbers as we go down, 20 over 90, 2 over 9.2222. Next number, 0.3111, and then 0.1889. And except for rounding, those guys should all add up to 1. So we can get a weighted average just by taking these proportions and multiplying by either the x or the y coordinates. And you're getting the same weighted average of the x or y coordinates. So an alternative method, and I've got a handout posted at the website which addresses this, whatever works for you. The first method, you get it and it works, you can shut down right now and not pay any attention to this. If you like this, it's a little shorter and easier to do as long as you calculate your proportions correctly. C sub x would then be 250, that's the x coordinate for Phoenix. And that x coordinate gets 27.78% of the weight, 0.2778. Add to that 350, the x coordinate for the next one, times 0.2222, and so on. 800 times 0.3111. And I don't know if the video is still getting all this off to the right-hand side. 850 times that number. 850 around our room, 0.1889. You have to do the proportion calculations up front, but that's a lot easier thing to punch into a calculator to figure out. It's doing the same thing mathematically. It's doing the same thing. It's kind of breaking up our initial ratio into 4 pieces. 250 times 25,000 divided by 90,000. Plus 350 times 20,000 divided by 90,000. We're doing the same thing. And I double checked when I punched that, I got the exact same number, even though these are really rounded slightly, 556.67. And when I do CY the same way, 250.2778 plus 125 times 0.2222. So on, using the other y coordinates, I came up with I'm off by 1/100th because of rounding here. 335.45 what I came up with. So I double checked. I think my work. I'm pretty confident that what I've got is accurate. Either one of those methods are going to work. And if you just understand it's a weighted average, you can almost kind of forget about formulas and just figure how would I do a weighted average of this, and that's how it's done. That's pretty straightforward. Everybody gets this. Nobody really has too many problems. On most exams, most students get this just fine. It's real straightforward. And that's all we're going to do on the logistics. And remember, don't forget to study for the concepts and everything still. But do a little bit on capacity planning. So we've got, for capacity planning, 2 kinds of problems you may look at. you may see. One is just like the book and the slides, where we are trying to calculate capacity utilization for a process where we have a set of equipment that is dedicated to one product. It's just very straightforward calculations. Then we have something you will see like the handout I gave on capacity planning when the equipment is shared to produce more than one product. And it has a different capacity for each of the products. So do a couple of those and I think we'll be done for the night. Or do one of each of those. And we'll be done. So we'll start with the dedicated equipment one, just like the slides. And for that, we'll go to the end of the chapter problem. So flip through your handout. We are past so it's going to be the next page after the centroid problem we just did. It will be labeled page 112 from the book. If we can look at problem number 4. This also is one of the practice homework problems at the website, and the solution for 4, 5, and 6 are all posted in detail there, but we can walk through 4 and talk about it here. So, as we read through it, always rain irrigation, determining capacity requirements over a 4-year planning horizon. Currently, 2 production lines are in place for making bronze and plastic sprinklers. Well, it doesn't tell us yet that these are dedicated equipment, but we'll get to it. 3 types of sprinklers are available in both bronze and plastic: 90 degree, 180 degree, 360 degree. So how far spread out the sprinkler will spray. And they have demand forecasts for 6 end items, or SKUs. So we want to figure what are our capacity requirements, our capacity utilization over the next 4 years. We still need to read some more. Both production lines can produce all of the different types of nozzles: the 90 degree, the 180, and the 360. The bronze machines needed for the bronze sprinklers. Now we finally get to indication where we have some equipment dedicated to some products. Bronze machines making bronze sprinklers require 2 operators and can produce up to 12,000 sprinklers each. They don't say that, but that's what they mean. The plastic injection molding machine needed for the plastic sprinklers. Okay, so we have another machine or set of machines for plastic sprinklers. Requires 4 operators, can produce up to 200,000. The capacity is 200,000 for plastic sprinklers. And finally, they tell us we have 3 bronze machines. Each one can do 12,000. We have 1 plastic injection molding machine that can do up to 200,000 plastic sprinklers. So we're set with 6 lines of data talked about in class how if you can compress that data down into fewer lines, the capacity planning is done a lot more easily here. So like the slide example, how can we compress this data in this problem here? How can we get it from 6 lines down to fewer than 6 lines? I'm just going to stand here until someone tells me. Chad, you got an idea? What would you do with this data?
To be honest, I don't know which one to run.
What's that? Oh, I'm sorry. I thought we were all on the same page.
Number 4.
We're looking for problem number 4. It would be the next page after that centroid problem. I'm on page 112 of the book. You're right there.
Plastic 90 with the bronze, or
Add the 90s together, the 180s together, the 360s together.
Okay, does the problem indicate that we can do that? What does it talk about machines and what they can produce?
it says they can produce different types of nozzles.
Any one machine can do any of the 90 or 180 or 360 degree nozzles. It's just different part that they're putting on, so it doesn't make a difference. What is the limitation on what a particular machine can do? So essentially, the question is be asking, let me look at one set of resources. What are the products that are being produced on that one set of resources, and you would collapse that data. Anybody? Says that we have bronze machines that can make bronze sprinklers.
Oh, so do all the plastics together and all the bronze together?
Yes. Okay, so we have one set of equipment that only does bronze. So that's how you separate the data out. I take all my bronze stuff, but it says that those bronze machines can make any of the different, the 90 to 180 to 360 is just a different piece that they put out. So the same capacity. So you can collapse all your plastic data down into one line by adding them, collapse all your bronze data down into one line by adding those together. And when you do that, I don't have the solution for that sitting in front of me, so let's start working on here. So we take the raw data and we collapse it over 3/4, collapse it or aggregate it together, sum up all the plastic, and in year one we're 50, 65, 97,000. Just leave it in no zeros there. That's plastic. And so now instead of having to do calculations over 6 lines, we can do them over 2. The second one, 44 and 16 is 60, 115. Doing this in my head, so help me if I make a mistake. 55 and 17 is 72, 136. And for the last year, getting busy, 56, 18, 74, 130, 141, I think.
Yes.
Yep, is that a yep I heard?
Yes.
Yep. Bronze should be a little easier, smaller numbers. So the bronze numbers, you collapse them 21. 12, 12, 24, 14 and 15, 29, and finally 28, 34. A lot easier to work with this. You could do it with 6 lines. You're just calculating 3 times as many calculations if you have to do it that way. So get our data as it's presented. There is our forecast of demand for each one of these 2 separate operations. We need capacity utilization, which is actual output. Well, we use our forecasted demand as what we think the actual output will be, divided by the best operating level, the capacity for that. The problem doesn't give us different capacity numbers, so anytime you see a problem that says the capacity is this, just assume that's the best operating level. And the only trick here is if there's more than one machine. So as we're reading this problem, we talk about the plastics. It says there's one injection molding machine that can do up to 200,000 sprinklers a year. Plastic sprinklers. So the capacity is 200,000. Because one machine, when they talk about the bronze machines, there's 3 of them. And the capacity is 12,000 each. 36. That's 3 times 12,000 each, where that came from. And that's simple from here. Calculating utilization numbers year by year is just the forecast divided by the capacity. Easy peasy. So the utilization for plastic, the utilization for the bronze lines, just ratios. I'll do a couple of them. We don't need to do the whole thing. Well, we'll do the whole thing so we can interpret and see what's going on. So somebody do the bronze ones. I'll do the plastic ones. 97 over 200. Our capacity just under 1/2. 0.485. We move over to year 2. 115 divided by 200, 0.575, and so on. 136, 168, 141, 0.705. for the plastic line, no real capacity issues or concerns there. Plenty of capacity for doing plastic. When the bronze line, can I have some numbers from somebody? What's the first year?
0.5833.
Point what? 5833? We'll just stop it at 3 decimal places. The next one should be, is that .6667?
Yes.
Yeah, 2/3. 667. The next one,
0.80555.
0.80555, we'll call it 806. Finally, we're getting 90 something here.
9444.
0.944. Okay. So crunching them is what you know how to do is a piece of cake. What to do with those numbers? No real issues. You might kind of flag this last one here, 94.4%. We're getting close to 95. We start pushing up towards 95 to 100%. Something that should get your attention. No real worries at this point in time. If our forecasts are good, we'll have sufficient capacity. This would be something a company should keep an eye on next year. When year 1 is done and we've gone through it, we have new forecasts for what are currently years 2, 3, and 4, and then we'll have a forecast for year 5. That'll be our new 4-year planning horizon in a year. We'll do it again, and we'll have different forecasts probably, and we'll see what the numbers look like and keep an eye on it. But for this particular situation, no immediate concerns for the company, only something to keep their eye on in year 4. That's straightforward, I think. You have any problems with that stuff? That's pretty cool. That's pretty easy. There are 2 problems I see from students regularly on this. Not multiplying the capacity times the number of machines, so putting a 12 in here instead of a 36. And then I regularly see, for some reason, they turn the utilization ratio upside down. And instead of 97 over 200, we'll do 200 over 97. It's not it. Remember, capacity, best operating level goes in the bottom.
Wait, do you times it by 3 because you had 3 bronze?
The problem says there are 3 of those bronze machines. It also says each one does 12,000.
Okay.
You see that? That's where the 36 came from.
Oh, yeah.
Other questions? Okay, almost at 2 hours. We will finish this up with one last example. So this one is in your handout as not from the book. It's just something I've made up because your book doesn't address this. So this is essentially the last page of the handout before formulas and everything. This is an example, capacity utilization problem for shared equipment. So we sit and read through this. Sample manufacturing is expecting to see increasing demand for their products. One of them is nearing the end of its life cycle, and you can look and see that it looks like the Econo version starts to drop off after year 4. What else is going on? As such, they're concerned about sufficient capacity. One manufacturing cell, so one set of equipment, produces a line of widgets. The Econo widget, standard widget, and the Primo widget. So one resource set producing multiple different products. We're sharing the equipment across different products, and the cell has different capacities for each. If it did nothing but Econo widgets, it could do 80,000 of them. It could do 70,000 of the standard widgets, if nothing but them. 50,000 of the Primo widgets, if it did nothing of those. But it's got to do all of them. So we need to calculate the capacity utilization of the cell from the various products for which the cell has different capacities for each of them. So I'll do a couple of years, and once we get a couple of years down, I don't think we need to continue working too many of them. So we have the Econo, the standard, and the premium widget. We got 5 years of data here, so this is, we break the mold of the class and do 5 years capacity planning. I'm just going to do a couple of them. So, year 1 and year 2, if you want more practice, do years 3, 4, and 5, and we'll finish those out. So, 20,000 is the demand for Econo in year 1, 25,000 in year 2, and so on. The standard, 25,000 in year 1, 27,000 year 2, and 14 and 15 for the premium widget. And then we could fill this out if we wanted to, but it's 2 hours. I think we're all getting a little tired at this point. Again, we need an expression of capacity, and the way we work these things is we'll figure out how much of the resources, in this case manufacturing cells' total capacity, is eaten up by each product. So we'll do a capacity utilization for each product and add those utilization numbers up to get the total utilization. So we need our capacity numbers. I always just write those off to the right. You can write them anywhere. But it was stated 80,000 Econo widgets, 70,000 standards, or 50,000 if it did nothing but the premium widgets. And so we'll do 3 utilization numbers in each year by product, and then you've got 3 numbers that are all the same unit, utilization. And we can add those guys together. Don't try and add up the demand and divide by the sum of the capacities or the average capacity or get the average demand. Don't do any of that. Calculate the capacity utilization for each product. So the utilization for the Econo, the utilization from the standard, and the utilization from the premium. And it's done the same way as for the dedicated equipment. Just take those numbers. For the standard, 20,000 divided by 80,000, that's 1 over 4.25. 20,000 is going to be the actual output of it, and that equipment could produce 80,000 of those. So we'll use 1/4 of its capacity producing the economy ones. For the standard, 25 over 80. I'm just dropping the zeros. Up. You should be screaming at me if you're watching this. Not 80. 70,000 is the capacity for the standards. And at the bottom, we would do 14 divided by 50. I know the 14 over 50 is 0.280. 25 over 70, I'm going to need my calculator for that. 0.357. So how much of the manufacturing cell's capacity is going to be consumed by all 3 of those products? Just add them up. 7, 5, 5, 8, 1, 6, 7, 8. 0.887, 88.7% of capacity in year 1. And then we just redo it for the second year, 25 over 80, funny 80, 27 over 70, 15 over 50, that's 0.300, 27 over 70, 0.386 if we round, 86. At the top, 25 over 80, I feel like I should be able to do that. Nope, 0.3125, round it off. Stick with 3 decimal places, round to 3. And add them up. 9, 1 and 8 is 9, 3, 3, 3, 9. Okay. Ooh. Year 2, we're already running into problems here. 99.9%. Essentially, year 2 is going to put us at 100% of capacity. We can calculate the rest of the numbers, but I can see that demand for all 3 products grows in year 3, so this is going to get higher. In year 4, our econo drops by 2,000. The other ones increase pretty significantly, so it's probably going to keep increasing as we go along and calculate those. So for years 3, 4, and 5, you should see something greater than 1 or exceeding 100%. And that's that. You guys feel confident with this one? Yeah, they're nodding their heads. No one's saying this, but everyone's nodding. So again, I think on exam 2, of all the exams, is probably the least challenging for students. Exam 1, the queuing stuff challenges students. In exam 2, the quality stuff is the toughest. The logistics and the capacity, I think, is pretty easy, pretty straightforward. Students typically do really well on it. Exam 3 is typically the most challenging, I think, for students when we do sales and operations planning and inventory management. But that's the next exam, so you don't have to worry about that this time. I think having sat through this, you'll be solid for the problems on the exam. Don't forget the concepts. Half of the points are just concepts and multiple choices. Questions? Anything? Marquita, you got any questions? All right. Well, yes. Wow, what do we got?
6 again?
What's that?
What number 6?
You want to do this, you said, or?
Yeah. Explain it to us.
One is pointing out, where are you? That was like the factor rating one? Problem
6.
Problem 6 in the logistics. Oh, you want me to talk about that some more? So problem 6 on the logistics was the factor rating system. We're missing some data. It disappeared. We lost those data points. Can we gain any information from the data that is left? So for those watching the video, if you understood that before, you can just stop right now. I'll take a couple of minutes explaining that a little further. So we have some data. They went through this factor rating process. They recorded their data, and a computer crash lost some. And so we have a number of factors. And in any factor rating system, each factor has a maximum points. That's kind of the weight that we give to that particular factor. And then we just did 2 cities. City X, whatever the hell they are, and City Y. They were, it may have been that they used the centroid method to try and find a good place to minimize transportation costs, and that point on a map is close to these 2 cities that have, reasonable transportation and that kind of stuff, so they went to evaluate those 2 cities. Maximum points for the factors, I'm not going to write them all out here, but for labor, it's 150 points, 130 for availability of utilities, and so on. 80, 75, 65. So going from most important factor down to least important factor, 40, 30, and 25. And then they've got ratings for the city. We have all the ratings. We kept that for City X. 130, 122, 73, 70, 59, 30, 15, and 22. We have most of the ratings for citywide, but we lost a few. 123, 110, we missed one, 63. We're missing one, 24. We're missing another one, and then down 17 at the bottom. So the question is all hope lost? Do we have to redo this process, or can we gain some information from this? And I explained it one way earlier by trying comparing how many, if we maxed out these 3 missing ratings for citywide, would that make up enough points to overweigh the lead that city X already has. So city X leads on every factor we have data for. So a short way, the way I did it was calculating how much is city X leading by, and then how many points could city Y make up if they max these remaining three. But a more straightforward way might be to say, well, instead of trying to do all that stuff, why don't we just say what happens, because we know that city X is in the lead, can city Y make up the difference by maxing everything else out? So let's just write a different color. Yeah, let's say they maxed out the remaining three. Add the numbers up and see what the score is.
Oh, it's still not higher than city X.
What's that?
It's still not higher than city X, right,
When you add them up, you'll find out that city X is still higher.
so, yeah.
Because what do the blue numbers give city Y? It gains them 7 points here, plus 6, 13 points, plus 15. It gains them 28 points. What is city X's lead? It's already 7, plus 12 is 19, plus 7 is 26, plus 6 is 32, plus 5 is 37. So it couldn't make up the difference. You'd find that out if you added both of those up and saw what they are. I don't have them added up, but you could do that. And you'll find out that city X has a higher number than city Y. So in that case, we could say, doesn't matter that we're missing that data, we know that city X comes out on top. Okay, anything else? A little over 2 hours. Hey, so that's it. Thank you for your patience. I hope somebody watches this, but at least you guys got to see it in person.